Welcome to the First Mold Insights, where we talk about injection molding, rapid tooling, product development, and real-world manufacturing insights. Today's topic is mold flow analysis for optimal injection molding. So, Alex, we talk a lot about design for manufacturing, or DFM, here at First Mold, and it's really about getting things right up front, isn't it? But sometimes, even with good DFM, you run into unexpected issues once you start molding. That's where mold flow analysis comes in, right? What exactly is it, and how does it help us avoid those headaches on the shop floor?
Yeah, that's exactly right. Mia, look, DFM is crucial. It's your foundation. But mold flow analysis, or MF8's like your crystal ball. It's an advanced simulation technique that uses CAE software, like mold flow or C-mold, to predict exactly how that molten plastic is going to behave inside the mold. We're talking finite element simulation of the whole process: injection, holding pressure, cooling, even warping.
Huh, okay, so it's not just a fancy graphic, it's predicting real problems? Like what?
Absolutely. Real problems. We can predict things like insufficient filling, where the plastic just doesn't reach every corner of the cavity. Those dreaded weld lines, which can compromise part strength and appearance, and warping deformation is a huge one. Being able to see these issues virtually means we can optimize the mold design before we cut seal. It avoids a ton of costly rework and production delays.
So it really complements DFM, then you're designing for manufacturability, and then you're simulating that design to catch the subtle flow issues DFM alone might miss.
Exactly. DoFM evaluates the overall manufacturability and cost, while MFA dives deep into the actual plastic behavior. They work hand in hand to ensure the product design is both feasible and opted for efficient, high-quality production. We use it a lot in automotive, aerospace, medical, you name it, any industry with complex plastic parts.
So, how does someone actually do a mold flow analysis? What's the basic process you'd follow?
Well, it starts with the geometry fist. You've got to generate a mesh from the 3D CAD file, usually an IGEs or STEP file, that kind of thing. Note edge quality is super important here. It needs to meet the analysis requirements. Too thick, you get inaccurate results. Too thin, and the computation time goes through the roof. It's a balance.
Right, so you're preparing the digital model. What's next?
After the mesh, it's all about material selection. Must software has databases with thousands of materials: thermoplastics, thermosets, even cooling media. You're inputting the material property model, things like viscosity models, PVT models, crystallization kinetic models, Plowis, specific heat capacity, thermal conductivity, mechanical properties. All that data is critical.
That makes sense. The plastic's properties are everything, aren't they? Then you move to the actual process settings, I assume?
Yep, Praiskin settings. You've got two main modes in most software: AE mode, which is for preliminary evaluation without considering a specific machine, and injection molding machine mode, which is for later validation, where you can input actual machine parameters.
Okay, so you can test it broadly and then dial it in for a specific press. What are the key settings you're tweaking there?
For filling, you're setting the fill time. The software often recommends one based on part volume and material. Where large or complex parts, you'd use multistage flow rate settings to get a uniform flow front. And then there's VP switching. That's critical. You're filling fast with speed control, but then just before it's 100% full, say 95% to 99% volume, you switch to pressure control. That prevents overfilling and flash.
Oh, so you're almost done filling, and then you ease off the gas, so to speak, to prevent defect.
Exactly. Then you move to packing settings. The purpose of packing is to compensate for any melt that hasn't completely filled the cavity, and crucially, to account for shrinkage after filling. We're talking segmented curves of packing pressure and packing time here.
And cooling? That's got to be a big one for cycle time, right?
Huge cooling time mainly depends on part thickness, but also melt temperature, mold temperature, and the thermal conductivity of the mold seal. We often use empirical formulas to estimate this, and you've got to set the cooling liquid parameters, ensuring enough flow rate to remove heat and maintain a uniform mold surface temperature for good part appearance.
So, after all that setup, you run the analysis, then you get a report. How do you actually read one of these reports? What are you looking for?
That's where the rubber meets the road. A good report starts with basic information: project number, resin, part number, cavity count, date, the software version, the analyzer. It'll also list key parameters like melt temperature, mold temperature, and the maximum injection pressure.
Max injection pressure, that tells you if your machine can even handle it, I guess?
Precisely, and the clamping tonnage too, which indicates the force needed to keep the mold closed. You'll see max and min melt front temperatures, giving you insight into the material's thermal behavior. Then there's the material data section: density, melt temperature, mold temperature, melt flow index. All essential for understanding the material's characteristics.
And mesh thickness diagnosis, I remember you mentioned that earlier.
Right? That section confirms we've balanced accuracy and computational efficiency. If elements are too thick, results are inaccurate. Too thin, it takes forever to run. We're looking for areas needing refinement, especially in complex geometries.
What about gate locations? That seems like a really critical decision you'd want MFA to help with.
It really is. MFA helps us evaluate optimal gate locations and sizes. We're looking at the filling pattern, making sure it's balanced and uniform to avoid issues like flow hesitation, weld lines, or air traps. It also impacts pressure and velocity distribution, cooling efficiency, and overall moldability. Sometimes, customers have specific requirements for gate locations too, based on aesthetics or function, so we factor that in.
Okay, so you've got the gate set. What's the output data that really tells you if it's going to work?
The fill time results are critical. They show the melt flow front expansion. You want a balanced filling process where the melt reaches all parts of the cavity at roughly the same time. This highlights short shots where material doesn't fill an area or hesitations where flow might interrupt. It can also point to overpacking if too much melt is forced into a path.
And nozzle pressure.
Nozzle pressure data helps us understand the flow front progression, any patterns, and how consistent the pressure is. Uneven distribution can lead to quality issues, like flow imbalances or air entrapment. It helps us optimize injection speed or melt temperature.
You mentioned clamping tonnage earlier. Is there a specific output for that?
Yeah, there's usually an XY plot of the clamping force. This shows how it varies over time, influenced by filling, holding pressure, and VP switchover. The big thing here is ensuring that the maximum clamping force doesn't exceed what your injection molding machine can handle. Exceed that, and you're looking at potential equipment damage or bad parts.
That's a huge one. What about those common defects, like air traps or weld lines? Does the report specifically call those out?
It does. Or air traps, the analysis accurately identifies where material flow converges and traps air pockets. If they're on the parting surface, we know we need exhaust slots or vents wise. We might need to adjust wall thickness or sprue position. Weld lines are similar. They form when melt fronts converge or separate and recombine. The report visualizes these, and we can then look at reducing injection gates or modifying gate positions or wall thickness to improve them.
And shrinkage too. I imagine that's always a challenge with plastics.
Oh yeah, volumetric shrinkage, or shrinkage volume, is key. It's the reduction in part volume from holding pressure and cooling. You want that shrinkage to be as uniform as possible throughout the cavity. If it's not, you adjust the holding curve to enhance uniformity.
And deflection? That's about warpage, right?
Precisely, deflection is the total deformation of the part. It's influenced by cooling factors. Rapid cooling can lead to uneven shrinkage and the inherent shrinkage of the material itself. Molecular orientation can also cause deflection if polymer chains align in a specific direction. The report will break down deflection into X, Y, and Z components, so you know exactly how the part is deforming.
So, it sounds like a comprehensive review. You're assessing everything from filling patterns to cooling efficiency, warpage, weld lines, air traps, pressures, and even gate locations. It's really about predicting every potential pitfall, isn't it?
It is the ultimate goal of mold flow analysis is to provide that theoretical basis for optimizing mold design, improving production processes, and predicting problems before they ever hit the shop floor. By doing that, we're building better molds, making higher quality parts, and saving significant time and money. It's an indispensable tool for modern manufacturing.
Thanks for tuning in. For more manufacturing resources or custom part production services, visit firstmold.com. We'll see you next time.